Hi, Andrea here. In the previous video, we explored more in detail the induction principle, focusing on the implications for the addition of natural numbers. Today, we are going to extend the knowledge about the implications of such principle, but this time considering the multiplication. Again, we need some basic properties to work on. A couple of ideas come directly from the definition of multiplication. Let's say n times m. This expression just says something like add the number m for n times. Given that the first basic property is 0 times n equals 0. This should be reasonable. If we sum n a null number of times, the result is null. Another case can be s of n times m. What is the result of this expression? Well, if n times m is taking the number m for n times, s of n tells us to take m one more time. So it is something like s of n times m equals m plus m plus m and so on. We can condensate this in the expression s of n times m equals n times m plus m. Here, the parentheses tell us the order of the operations. The first operation to perform is inside the parentheses. For convention, multiplication is performed before addition. Right now, we are in the same position we were in the case of addition. We would like to prove the inverted relations. In other words, is it true that n times 0 is 0? Again, this is just 0 plus 0 plus 0 for n times, and so the result is 0. What about the other formula? N times s of m equals n plus n times m. Guess what? We use induction. Let's see if our formula works when n equals 0. As usual, considering m fixed to a generic value. We get 0 times s of m equals 0 plus 0 times m. Every term is 0, thanks to the first basic property of multiplication, and thanks to what we know about addition. So far, so good. After that, what about the successor of n? Considering the starting relation as true. The formula becomes s of n times s of m equals s of n plus s of n times m. First of all, we can work on the left-hand side. By the second basic property of multiplication, we get n times s of m plus s of m. Now we can use the starting relation, remember we are assuming it true in this case, getting n plus n times m plus s of m. The right term becomes instead s of m plus m plus n times m, again using the second basic property of multiplication. The two expressions can seem different, but we got the same multiplication, the same numbers, and we are counting forward by 1 on both sides. Therefore, the proof is finished, and we call these two equalities lemma 1 and lemma 2, for multiplication obviously. Now, we have these two new lemmas, and we can use them to prove the commutative property of multiplication. N times m equals m times n. As always, to prove it, m is fixed and we start using n equals 0. The expression becomes 0 times m equals m times 0. Given the properties of multiplication, we have just found both sides of the equality are 0. Now the next step. What if we substitute n with s of n? We get s of n times m equals m times s of n. We get, using the other two previous properties, that n times m plus m is equal to m plus m times n. Here, as usual, we are considering what happens given the property n times m equals m times n true. So we can change the equality into n times m plus m equals m plus n times m, and it is verified thanks to the commutation of addition. As a last remark, keep in mind everything we touched here derives from the sum operation and ultimately from counting forward using the successor operation. Wonderful! We are getting used to think in the right way. As in the previous video, there are other important properties to cite. These are super important and you can attempt, well, to prove them. But don't worry, take your time and give it a try only if you want.